Welcome to EE251 PreLab Guides. This is Professor Hiren Trada, and in this video, we're going to look at PreLab number 8. Lab 8 for EE251 deals with AC power. AC power. Now, why is AC power important? Well, AC power has to do with the power that flows into and out of an inductor and a capacitor. So if we here take a look at the title of the lab, we have AC steady state power, power triangle, and power factor correction. So AC steady state power, power triangle, and power factor correction. So again, as I was saying, why is it important? Well, because it deals with the power that is associated with the inductor and the capacitor. So let's talk a bit about the fundamentals before we get into the lab and the pre-lab itself. So here, if we have a circuit, let's say that AC power is being applied and you have a load. Load comprises of an inductor and a resistor. Okay. Now this is AC voltage. And of course, you'll have some current I flowing through the circuit. Now what happens? A resistor, of course, well, receives AC voltage and current and behaves exactly the same way as it does for DC. So it dissipates power in the form of heat. So the power associated with the resistor is noted by P, and the units is watts. Okay. The power associated with the inductor, however, is noted with the letter Q. The reason is it has to do with the reactance of the inductor. Okay, so AC power transmitted to an inductor has to do with the reactance of the inductor, and it is noted by the letter Q for reactive power. Reactive power. It has unit of volt ampere reactive, VAR. Okay, reactive power. Now, similar to the mathematical representation of reactance using the imaginary number J, we use the same concept to mathematically describe reactive power Q. Okay, so we say reactive power Q is imaginary, but it's not imaginary in real life. It has a physical basis, it has a physical presence, but the mathematical representation is imaginary, and hence it is referred to as imaginary. So do not be confused when you hear or read the words imaginary power. Okay, so reactive power is imaginary, just means a mathematical representation. But here is the big difference. The big difference is that when you have an inductor or a capacitor for that matter in a circuit, the reactive power associated with their reactances do not do any real work. Okay, so the reactive power is not doing any real work. It is mostly there to set up the magnetic field in that inductor. Okay, because it's associated with reactance. The real work of converting the electrical power into useful, let's say, mechanical energy, like so electrical energy being converted to mechanical energy, is done by the real power P, and hence this is also known as real or average power. Okay, real or average power. So think of this as a combined load where you have to require P as well as Q. And P plus Q, and Q is imaginary number J, is referred to as S, where S is total complex power. Total complex power. So if you were an industrial customer, you would be running electric machines sometimes 24/7. Electric machines have windings and they have coils, and those windings and coils are nothing but inductors. Okay. So industrial customers have huge, big electric machines that have inductive loads. Okay. Industrial customers have inductive loads, and that's why study of AC power is very important. Okay. So what happens is the utility company has to send P as well as Q over the transmission lines to the industrial customers. But what happens is, in an inductor, of course, energy flows in, and then when the negative cycle comes around, the energy flows out. So that means that the utility company sends, so utility company sends P plus Q to the industrial customer, and then the customer sends the Q back, right? Reactive power is associated with the reactance of the inductor. In the inductor, in the positive half cycle, especially for AC, the energy will flow in and in will flow out. Okay, so it's constantly flowing in and out of the inductive loads. Important to remember that is reactive power is not doing any real work. The real work is one done by the average power, and hence it is also known as real power. So the reactive power, even though it is not doing any real work, still has to be transmitted over long distance transmission lines. And that is not desirable. So anytime you have electrical energy transmitting over long distances, the wires and the conductors heat up and there is tremendous loss of energy. Also, in order to send this huge amount of reactive power, the wires and the associated equipment has to be able to withstand all those high currents and voltages, again, which is not highly desirable or cost effective. So in order to prevent that, we use what is known as power factor correction. So let's talk about what power factor is and what the correction means. Okay. So since inductive power depends on the reactance, not depends, or is associated with the reactance, and it is a complex quantity, the inductive power Q in the complex plane is plotted with a plus 90 degrees. If you remember, ZL, impedance of an inductor, has a positive phase, ZC has negative. And so when you plot it for a capacitor, QC is minus 90 degrees. Okay. So power factor has to do with how much reactive power is required by the system. Okay. So we talked about total complex power S is equal to P plus JQ. These are rectangular coordinates, right? Rectangular coordinates. So if you plot this on the on the complex plane, P would not have any phase, and so it's lying on the x-axis. QL is lying with plus 90, and so this would be the real axis, this would be the imaginary axis, and joining the two sides of the triangle would be the magnitude of the total complex power. The phase angle that it makes with the real axis gives you the phase of that total complex power. So again, S is equal to P plus Q, and you plot this, or you convert this into polar coordinates, you get S is equal to magnitude of S to the phase angle theta. This phase angle theta is known as the power angle, and it is simply the phase difference between the voltage and the current, theta V minus theta I. And cosine of this angle is described by the term power factor. It's a right angle triangle, so think about what that means. The higher the angle, the larger the angle, the larger is the requirement for QL. Or you could say the other way around. The more the requirement for reactive power, the larger is the angle, right? If Q requirement is here, then the angle is larger. If the Q requirement is down here, the angle is smaller. So it is desirable to have a very small angle so that you don't have to transmit all of that reactive power. And the process of lowering the requirement of this inductive reactive power is known as power factor correction. Because if your inductive power requirement is completely zero, then theta is equal to 0. So power factor, which is cos of 0, will be 1. And that is the highest value for a power factor. It is also stated in terms of percentage. So highest value for a power factor would be 100%. For any other value, it would be less than 100%. So how do we do power factor correction? Well, we use a capacitor and we connect it across the inductor. So what happens is, if you connect a capacitor in parallel or in front of that inductor, once the reactive power is transmitted and the energy flows into the inductor, after that, in the negative half cycle, when the energy flows out, it flows out into the capacitor. And then the next cycle, when the inductor requires reactive power, well, instead of it coming from the utility company, the capacitor will send it back. Since capacitors and inductors are duals of each other, in one half cycle, the energy flows out of the inductor and into the capacitor. And the next half cycle, it flows out of the capacitor and into the inductor. So the total requirement for the reactive power is reduced because now the requirement is self-contained. It's coming from within the system itself. Okay, so it is being provided by the capacitor. After the initial requirement, once the energy is received one time, after that, the energy is stored in the capacitor and it keeps bouncing back and forth between the L and the C. And so that process is known as power factor correction. In terms of the power triangle, this is what it should look like. You have P and you have certain requirement for QL, right? QL. QL, this is what is required. Well, you connect a capacitor and then the same requirement is brought down. And this would be QC. Remember, it's a vector. So vectors, when you apply law of conservation of energy and you're adding up all the vectors, you're starting at the endpoints. Anyway, so if only QL was present in the circuit, this is your requirement. But now with QC, your requirement or your angle is now very, very small. Okay, and that is power factor correction. And that is what you're doing in today's lab. So let's look at the questions. PreLab question, let's see. PreLab question number 1. You're asked to construct the power triangle for the inductive load, asked to determine the real power, reactive power, apparent power, and theta. Also find the power factor. So if you look at the lab 8, all of the equations are there in the lab 8. And so right there in lab 8, So as usual, if we scroll down into the background, it tells you all the information that you need and all the equations that you need to solve for the questions. So all of the equations that we learned about in chapters 1 and 2 for power still apply, but the format is a little different. Okay, here you can see P is equal to I square times R. P is also equal to V square over R. Okay, we still use the same equations, but now because it's AC, we have to use the RMS values for the voltage and the current. Okay, we have to use the RMS values. So it's V RMS square over R and I RMS square or times R. And the same applies for the reactive power Q. Reactive power Q uses the same equation, I square R, but because Q is associated with the reactance, we substitute R with X, and hence Q reactive power is I RMS squared times X. If we're trying to find for inductor, it would be XL. If we were trying to find for capacitor, it would be XC. And in terms of voltage, it would still be Q is equal to V RMS square divided by X. Okay. Complex power is the total complex power, meaning the sum of the voltage, sum of the real power and the imaginary reactive power. Okay, reactive power. So S is VI, half VI asterisk. Now, here it gives you the equation, which is VRMS times IRMS asterisk. That asterisk denotes complex conjugate of the current, and complex conjugate is simply the opposite of the complex number. Okay, so it is A plus JB. The complex conjugate becomes A minus JB. If it is in polar form, if it is R with the phase angle of theta, it becomes R with the phase angle of minus theta. And that is the complex conjugate. So the product of those numbers, VRMS and IRMS asterisk, gives you the total complex power S. S is also P plus JQ in terms of real power and reactive power. Okay. Now, when you have all of those quantities, you can create the power triangle. The magnitude of S, which you see right here, magnitude of X, which is the hypotenuse of the right angle triangle, is also known as the apparent power. The units for apparent power and for total complex power is volt ampere, VA. Okay, so in our circuit, we have, let's go back to the question. We have a source. That source is supplying 10 volts RMS and 60 hertz, 10 volts RMS and 60 hertz. And we have a source impedance ZS. We are treating ZS with equal to 0, so we would ignore that. Inductor value is 159 millihenry and resistance is 30 ohms. So let's see how we can solve for all the quantities that are asked of us. Okay. What you would do is you would simply take all the information that is provided and compare it to the equations that we have available in the lab. So the first thing to do, all right, let me change. Let's change the view. Let's go here. Okay. So as I was saying, the question is to find the real power. So PreLab 8. Oh, PreLab 8. Okay, let's question number 1. Yes, to find real power P, reactive power Q, apparent power, which is magnitude of S, phase angle for the power triangle, which is theta, and of course, power factor. What we are given, is value for L. We're given R. Let's write it this way. 159 millihenry. R is given as 30 ohms. And our V in is given to us as 10 volt RMS. Frequency F is 60 hertz. So the equations that we have will allow us to solve this problem. So first thing we want to do is, of course, we want to find the total impedance in the circuit. Okay, total impedance in the circuit. The total impedance in the circuit would be given by Z total would be equal to R plus JXL. Okay, R plus JXL. And XL, of course, is omega L, or omega times L, or you can write 2 pi FL. Okay, 2 pi FL. Once you have that total impedance from the XL, you find IRMS, the magnitude of IRMS. And that would be given by simply VRMS divided by the real value of R. Now, when you find the real value of R, what you have to do is you have to, actually it's not R, it should be magnitude of Z total. That would avoid the confusion. So you would get magnitude of Z total with a phase angle theta Z. Okay, so IRMS would give you VRMS divided by Z total, or magnitude of Z total. So you would get the current. And once you have the current, you apply the equations for P average, the average power, QL, and magnitude of S, and of course theta from the lab 8 background section. Well, that's it. That's how you would solve. Once you have the values, you should be able to draw out the power triangle. Okay, you should be able to draw out the power triangle. Now, question number 2 is very similar. The only difference is in question number 2, now ZS, the source, has some impedance, which is 50 ohms. So all you would need to do is you would actually add that impedance in your equation for Z total. So ZS is 50 ohms. So let's see how you're going to do that. Simply take that 50 ohms. Again, note that it does not have a complex number in there. So ZS is purely resistive. Okay, ZS is purely resistive. And so if it's purely resistive, well, all you have to do is you add it up. And so in this case, your Z total would be ZS plus R plus XL. Now ZS, again, it's just given to us as 50 ohms. So add up in this expression, you just plug in the values and add up all the real components and add up all the imaginary components. And then again, you would find magnitude of Z total and the phase angle. Okay, it will be different from the one earlier because now Z has actually does have a value. In the earlier one, ZS was equal to 0. You apply the same equations as above, and you solve using the same equations. Okay, you now have a different power factor when you take the source impedance into account. All right. Now, question 3 actually has, let's go back to it here. It's asking for power factor correction, right? So for circuit number 2, meaning right here, question number 2, you're required to do a power factor correction. It's asking you to determine the capacitance in parallel with the inductor resistor combination to correct the power factor for circuit of question number 2. Essentially, what it's asking you to do is this. Let's see. Okay. So question number 3, and Let's scroll down a bit. You have a source, you have ZS, and you have a resistor. Actually, let's say inductor first. So let's do inductor, a resistor, and then it's asking you to plug a capacitor in a parallel. Okay, it's asking you to find the value of this capacitor to reduce that power factor. Okay, to correct the power factor, meaning go all the way to 0. Okay, correct the power factor. Now, inherently, there is a slight error built into this question. And well, it's not an error as much as an assumption. So you would have to assume that you're going to increase the voltage. You're going to increase the voltage across the inductor and that resistor. Okay, inductor and the resistor. And so by assuming that, you can change, sorry, not you can change, you can assume that the voltage across R plus L is the same as R plus L in parallel with C. Okay. And this will allow you to set QC is equal to QL, which you obtain from question number 2 above. Okay. And that's the assumption you have to make. Otherwise, you cannot solve this. You cannot solve this problem. Okay. You have to make that assumption. So once you assume that, you said QC is equal to QL. Again, remember, the whole purpose is that the reactive power requirement for the inductor should come from the capacitor and not from the source itself. So after that, the equations that you would need is this. QC, you can write as VC square or XC, right? So you calculate XC. You solve for XC. XC can be written as 1 over omega C or 1 over 2 pi F C. Then you solve for C. And that's it. That's all you have to do. Okay, it's 3 equations, 3 steps. But the important thing is you have to make this assumption at the beginning, without which you will not be able to solve this problem. And well, there you have it. That's power factor correction. So hope this helps. Reach out to me if you have any questions. htrada@calpoly.edu. You can stop by my office anytime you want. I'm usually in there and my schedule is printed outside. Good luck. Good luck with the pre-lab. Good luck with the lab. Well, again, reach out to us if you have any questions.